Okay, so the first thing is talking about what is the virtue of a model, not the bikini kind. Um, think about the modal model, this example that we've been discussing throughout kind of this course so far, and adding additions to. How is a model useful when talking about science, when talking about education, computer programming, new uses, etc., and how could it possibly be detrimental? So I'd like to talk to some of you. What do you guys come up with? So what about the modal model? Do you guys think that you learn from it? Is it useful in that way? Nobody? No right answer. I'll tell you what I think. What a lot of people think. So there's a famous quote: if you start one way and keep going through the thing, you have to see models. All models are wrong, some are useful. Basically, the idea that we come up with these really simplistic versions that we can easily put into a PowerPoint for these complex cognitive issues. Based on them being perfectly replicating what's happening. In a lot of ways, it's going to be wrong. You can have experiments that would verify it in some ways, and then you come up with a new experiment and something is flawed, and you totally counteract that original model, and then everybody pays their time for that, etc. So it can be useful. We can redesign these models, but they're flawed. Yeah, well, it's kind of what we said about the starting point. So the long term, so we can't put on some hardware, so we just have digital things and like try to make it focus now. There could be external sources that are different for different uses. That's a great point. They're making it fit the model. If you have something that you want to be correct because it's easy to follow, and also if you get this corrective phenomena where scientists are really happy and let their idea last and the important one. So you start to try to follow the information so that it fit this. You're really just biasing the science. So let's talk about what's going to be yeah, right. You want to just pick that or it doesn't get into mainstream. So these are important issues to keep in mind. Just want to go through the syllabus, refer you to this real quick. So next week we're going to start talking about long-term memory, chapters 6 and 7. For paper approval is due next Tuesday. So come up with what the article that you want to read, cognitive type of article, send me an email. That's the easiest way. I'm just going to mark your username and make sure that you have sent it in for that assignment. And then we're going to have a review for the exam on next Thursday, so covering what we've covered since the previous exam. So vision, working memory, long-term memory. So then your exam will be posted on the Thursday of next week. You will have 2 weeks to complete it because the week next, 2 weeks from now is spring break, so you can do it over spring break, but I won't make you, so you still have the week that you normally need in to complete the exam. Same format, online. Yeah, try to make the questions. I'll try to make sure the questions are more fair this time. Do our best. Might be a curve, don't know yet. There you go. Any questions so far about that? Nope. Okay. Okay, so we're going to cover what we hadn't covered last week. Just checking. Okay. So yeah, continuing our chapter 5 lecture from last Tuesday. So this is the slide that we ended on. It's the summary of what we so far had learned about sensory memory.
So sensory memory, if you remember, is kind of the first step. So feeding the information in. We get all of the information into this hypothetical model store, which has a very big capacity, a very large capacity. Hypothetically, it's unlimited. It's every bit of information that's funneled into our minds at that point. But the duration is very short. In some instances, less than a second for visual information, a little bit more than a second for auditory information. This register, it keeps in that information, the sensory information, in order to transmit that into our short-term memory processes, which can store some of the information for a little while. That stored information in our short-term memory has an interplay with our long-term memory. So it can store that information. You can also recall information from your long-term memory into your short-term memory to be able to work with it. So that was sensory memory. Now we're going to just talk about short-term memory from your book. So back to the 1968 model, this second step after the sensory memory. So input fed in, you got your sensory memory, whatever thing you're paying attention to is sent to your short-term memory, where you get that rehearsal, so that control process, some of those that you can be using, like repeating the word, like the memory palace thing I was talking to you about, so different strategies. I did put that TED Talk up under the course content, under the section that we're talking about, so take a look at it. It's actually really cool. I know, school learning might not be the most fun for you, having additional stuff, but I would definitely recommend it. It's kind of a neat idea. Maybe some of you want to maximize your own memory capacities. This would be a good thing to start to look at. Anyway, short-term memory. What is short-term memory? Short-term memory holds a small amount of information for a short time, a little bit more than that sensory memory, but it stores what you are currently processing. So it has a limited capacity, and it stores those pieces of information for a short amount of time, but you're processing them, you're working with them. A big proportion of the information gets lost from that sensory memory input. You can't be paying attention to all of that information, just our brain's limitations. So a lot of that is lost in our short-term memory, is that intermediate step, so it connects your sensory memory and your long-term memory. So short-term memory is also short. It has a short duration, as you would imagine from the name. This was an experiment where people were told to listen to a stream of 3 letters, and then you have to count backwards by threes for duration of seconds. So after 3 seconds, they were told to remember the 3 words and verbally say the three letters. So they would verbally repeat the 3 letters, and then again at 18 seconds later. And this is basically the percent of correct letters that were remembered by the people. So you can see a sharp decline. The first figure on the left, this was the average of that experiment. You lose a lot of information as time goes by. Takeaway message, it has that limited capacity. But then somebody else took a look at the experimental findings and found another interesting phenomenon in that the first trial that the participants had with the remembering the 3 letters, the first trial, there wasn't a huge difference in what was lost between the 3 seconds and the 18 seconds. But later on, so they go to the third trial, and there starts to be a decline. And as you continue with the experiment, the entire amount of trials, the average becomes very low. So basically, you get worse at remembering at 18 seconds as time goes on. So what might be causing that? It's so this is proactive inference, that sort of experiment. So the previously learned information interferes with your task as it goes on. If you keep remembering a string of 3 letters, each time you add a new string of 3 letters that you're remembering, it starts to get a little mixed up in your brain. It's the same type of stuff, so it's interfering with your ability to remember. So participants, as I said, performed very well in the first trial, so about the same between the 3 and the 18. And their performance dropped from the third trial onwards. So the triplets of letters were stored in the short-term memory for some amount of seconds accurately. And then as the trials continued, the previously learned content interferes with the new content. So the inference effects are present for 15 to 20 seconds. That was sort of another experimental finding, that if you are predisposed or you're exposed to these things that create the information interference, the effect of that is about 15 to 20 seconds. So after that, you're going to forget about that information. So the interference effect decreases after that 20-second mark. So if I gave you the first trial of that experiment, continued that experiment, then waited 20 seconds before beginning another trial, that information interference would go away, essentially. So the conclusion of that would be, think about this. The effective duration of the short-term memory is about 15 to 20 seconds. So that would mean if you've got some amount of information stored that can interfere with other information within your short-term memory, if that effect goes away after 20 seconds, that kind of gives you an indication of how long things can stick around in your short-term memory, even without your want of them to do so. Does that make sense? Any questions? I think these experiments are really good at conveying the information in this. And think about, too, like, when you're constructing an experiment, you are the first or close to the first to come up with these ideas. It's interesting when you, like, take your concept that you're trying to flesh out, and then you somehow try to convert that into an experimental procedure. So I don't know, it gives you some appreciation of the cognitive science. So I think it's good to remember. Here's an example from your book. This gets at the capacity of short-term memory. So it has a limited capacity. You're only able to keep some amount of things within your short-term memory to be working with them at a time. So I guess, see if I can do this. Essentially, take a piece of paper, cover these numbers up, and take the paper, slide it down one, memorize those numbers, pick the paper back up, and say those numbers. And keep doing that as you go on. And the last line that you're able to replicate. So you can do the third line, but at the fourth line, you're forgetting some of the numbers, you're not accurately reciting them. That tells you your digit span, so how many things you're keeping in your short-term memory at a time. So that's your personal best type thing. The typical for most people is 5 to 8, 5 to 9 things that are within their short-term memory, so I guess 5 to 8 experimentally for digits. So that kind of tells you that the average person has a capacity of 5 to 8 items within their short-term memory. So generally, short-term memory is 7 plus or minus 2, so 5 to 9 things kept into your short-term memory at a time. But also the size of the items, it can be variable, the things that are stored at a time. So think about this list: monkey, child, wildly, zoo, jumped, city, ringtail, young. So 1, 2, 3, 4, 5, 6, 7, 8. 8 variables that would be stored in your working memory at a time. So you'd be able to theoretically memorize this list, and then I'd cover it up and you'd be able to tell me all of the words just from memory. But there are other strategies to be able to do this more easily. So you can vary the size of these items that are in your short-term memory by this process of chunking. So instead of thinking about each individual word, you can combine them as follows, things that are meaningful. So a ring-tailed monkey, jumped wildly, young child, and city zoo. So now instead of 8 things, you have 4 things, sorry. You can go a step further even with these types of sentences or these types of variables. And in this case, you can combine everything into one sentence. So you'd effectively have one thing stored in your short-term memory. The ring-tailed monkey jumped wildly around the young child at the city zoo. So that's sort of the idea is you can develop these strategies for making all of the items that you need to remember available to you more easily. So this is the idea of chunking, collection of elements that are strongly associated with one another, but are weakly associated with elements in other chunks. So that would be the effective boundaries of those chunks that you've created. So in your mind, sticking 2 things together, but not having that interfere with the other things that are stuck together. So small units can be combined into larger, meaningful units. Chunking as a strategy to expand your capacity of your short-term memory, and then instead of items, chunks or units are handled within the short-term memory. So those are the variables now. So there's an experiment, or there are some experiments, this is discussed in your book, the effect of chunking. So they took beginner and master chess players and showed them a chess board and told them to memorize how the pieces were set up. So the masters would have the image of the chessboard. They would be aware of certain strategies or configurations that were common to chess. So if you're playing an actual game of chess and then you take a snapshot of that chessboard and you show that to a master, it's going to be meaningful to them in certain ways. They are able to kind of chunk that information together, whereas a beginner, it's just a random configuration on the page or on the chessboard of that information. So it kind of shows you the ability of chunking. And then you compare that to if you just have the chessboard, instead of having an actual game being played, you just randomly organize the chess pieces on the board. It basically it eliminates the master's ability to form these chunks because it's no longer meaningful. It no longer has that chunking effect, or not it so easily. So that effect goes away entirely. So short-term memory, how is the information coded in short-term memory? So different modes of information are coming in. You have the auditory coding would be sound, visual coding would be images, and you have semantic coding, which would be the meaning of those messages themselves. So there is a physiological approach when you're thinking about this. The stimuli are represented by neurons firing, but as you remember, neurons are coded to specific things. So you have neurons that are coded towards those auditory, towards those visual, towards the meaning of, the thing that you're taking in. So here is an experiment that suggested that your short-term memory seems to prefer auditory information if you were reading words off of a page or letters. And the way that they went about showing this would be that target letters were flashed on a screen. So you'd have a blank screen and then you'd have a letter that was presented to you. So participants had to write down the letters on the screen, presumably once they had committed them to memory. So there was a effect was misidentification of letters that had the same sound to them. So F, S, X, in your verbal description, your auditory understanding of those, they're very similar. They rhyme. On the phone, you have to always say S as in Sam, that type of thing. So the fact that they were interfering with each other suggests that even though you're seeing these images, it wasn't the visual of the image that was being represented in your short-term memory. It was that sound, S, X, F. So that kind of gives you some evidence that it's more of an auditory coding within that short-term memory. Here's another experiment that also showed this type of effect. So they asked native Chinese speakers to memorize or to look at these these characters, so it'd be the same type of experiment as memorizing letters. So instead of letters, you had these symbols that indicated some information about like a sentence, but didn't have any kind of verbal meaning. So they didn't have a sound associated with them. They were just present within information. Versus you had characters that actually had a verbal sound associated with them, and had people remember these and then recite them or write them down, etc. The effect is that the radicals, these things that didn't have a verbal sound or an auditory sound associated with them, were remembered a lot less accurately. So it gives you a little bit more evidence that even though it's not spoken, a written word on a page, you're still coding that as if it were auditory information and working with that within your short-term memory. So here's a different type of evidence. So that was auditory. Now we have semantic coding. That would be the meaning of these things. So here's an experiment. So some participants in trial 1, so the first group was the fruit group, the second group was the meat group, and the other one is the profession group. So in the trial 1, each group was given 3 words associated with that concept. So banana, peach, and apple are fruit. Salami, pork, and chicken are meat. Lawyer, firefighter, teacher are professions. So you had 3 trials where people remembered these words. So you remember a new set of 3 words each time. But then in the 4th trial, all of the groups were supposed to remember fruits, different types of fruits. So the meat group had orange, cherry, pineapple, so did the profession, which was different than the semantic words that they had before. And the results of this experiment were that, so let's see, different groups. You can kind of take a look at this. I guess the last group is really the meaningful information. So you have the same type of effect. The meaning gives you that interference effect. So once you've remembered a group of 3, the next time you have to remember a group of 3, there's already that stuff within your short-term memory. So it's giving you that interference effect. But when you look at the last trial, the people in the fruit group had the same interference effect, but the people in the meats and the profession group didn't have that effect because it wasn't the same overall concept. So instead of remembering a third group of professions, they now had fruit, so they didn't interfere with each other. So that gives you a little bit of justification or information about maybe there's also something about the meaning that's influencing the chunks within your short-term memory. So not just the verbal words, but the actual semantic meaning of these words that you're taking in. So to summarize what we've covered of short-term memory so far, short-term memory has a limited capacity, 7 plus or minus 2 chunks, so it could either be the letters or it could be the words that are composed of the letters or the sentences composed of the words, etc. The duration of your short-term memory is 15 to 20 seconds. That's the point that interference effect drops off, so it gives you a little bit of justification there. Short-term memory stores information for a short period of time. It processes the information. It's what you're kind of using to make decisions and work. And chunking can be effective to expand that capacity of short-term memory. Information coding in the short-term memory. There is auditory, there is visual, there is semantic, but things like words are going to be coded instead of visually auditorily. Okay, so now we're going to talk about working memory a little bit. So working memory was proposed after sort of that modal model, after this concept of short-term memory, and there are people that want to totally remove the idea of short-term memory and replace it with working memory, because working memory can be decomposed into more units that we can study and understand. So here's participants are able to do more than one thing while processing information within their short-term memory, which tells you a little bit about maybe there are different chunks or different elements that are able to deal with that information at a time within that whole concept of your short-term memory. So here, participants can perform 2 tasks in parallel. So you're reading this sentence while keeping these numbers in your mind. So you're rehearsing to yourself 7, 1, 4, 9. You're keeping that stored within that short-term memory, but you're also reading this paragraph, and people are able to perform that. So it shows you that a couple things can occur at a time. So short-term memory consists of these components that function separately. So that's why we want to replace that concept with working memory. Working memory is a limited capacity system for temporary storage and manipulation of information for complex tasks such as comprehension, learning, and reasoning. So it differs from short-term memory in that short-term memory is a single component, whereas working memory consists of a number of different parts that we can conceptualize in a model. Short-term memory is concerned mainly with the holding of information for that brief period of time, whereas working memory, we can talk about more the manipulation of information that occurs during these tasks. So these complex cognitions, decision-making type stuff. So here is a model proposed for working memory. So on one side you have the phonological loop. So it's your verbal and your auditory information. And the other side you have your visual spatial sketch pad. So that's your visual information, your visual input. And in between them, something that works in between is that central executive. So that's kind of where that work is happening. So here are sort of examples of what we're looking at within these different sides of the working memory model. So the phonological loop would be your reading or you're listening to somebody. In another example, your visual-spatial sketchpad, if somebody's looking on a table and solving a puzzle that's not exactly a verbal or an auditory task, so it would be your visual working memory capacity dealing with that. And then that central executive sort of takes information from both of those sides and allows you to work with it at a time. So the central executive is where the major work of working memory occurs. Pulls information from your long-term memory, coordinates a phonological loop and the visuospatial sketchpad, divides your attention between these 2 types of tasks. So people are able to fairly easily or fairly well do 2 different tasks at a time as long as they're, those 2 different sides, the phonological or the visual. Like here, the example is somebody driving a car. They're looking at the road and they're able to do that visual stuff, but they're also able to listen to the person giving them directions.
So is this like related to multitasking too, or is it like short-term or just working, or? So multitasking, yes, you also do 2 different tasks that rely on both of these, sort of each of these kind of independently. So multitasking, there's a lot of interesting experimental work. There are a lot of people that say nobody can truly multitask. So they would be do 2 different tasks that rely on both of these at a time. So instead of multitasking, while you might be observing somebody multitasking, they're actually task switching. So they do one task, take a break, do the other task. So it seems as though they're doing both at the same time, but their mind is actually only processing one at a time. That's a really good question. It's interesting stuff to study. And whereas a model might tell you that somebody is at the same time parallel processing and truly multitasking, it took experimental evidence, different people theorizing and creating experiments to take a look at that. So here kind of gets at even that multitasking stuff. If you are so slowly read the following letters, look away and count to 15, and then you write them down. Or sorry, working memories or the multitasking will be another page. But this is basically in
an effect of having things that are similar and screwing with your ability to perform that task. So if you were to perform this with each of these lists of letters, G, C, B, T, V, P, they're very similarly sounding, so it's going to interfere with your ability to perform the memory or keep them in your short-term memory and write them down. Whereas if you have letters that aren't rhyming your phonetics of them, F, L, K, S, Y, G, it should be easier for you. Same thing with word length. The first line is one syllable words: beast, bronze, wife, gold, inn, limp, dirt, star. Whereas the second list is alcohol, properly, amplify, officer, gallery, mosquito, bricklayer. So it should be more difficult to remember the words that are longer. So even though you can chunk, it's basically that if it becomes more complicated, it's still a little more difficult to work with. So here's a task that sort of gets into that multitasking or the different sides interfering with each other. So if you were to memorize the sentence above, John ran to the store to buy some oranges. So if you're memorizing that sentence and then while you're remembering that sentence, you're going through it in your mind, you say yes for every word that's a noun and no for every word that's not a noun. It becomes a little difficult. There's sort of that interference effect of these are both verbal or auditory tasks. Whereas you're if you're memorizing the sentence, and then for each word, noun or not, instead of verbally or in your mind auditorily presenting that, you just take your finger on a page and point to the yes or the no. So one would be the auditory and one would be the visual or the spatial. It becomes easier for you to perform. So the idea is that your phonological loop would be overloaded in the first condition. So that would be kind of that multitasking, as you have that limited capacity within that loop. If you're doing a few different tasks at a time that are both demanding of those resources, it becomes more difficult. Whereas if you're breaking that up into those two different modes, it becomes easier for you to perform. So it actually gets into kind of some human factor stuff, which you guys might find interesting. If you're creating technology for people, this is something to keep in mind. If you're, for instance, um, having a navigational system, like it's called a heads-up display, if you're presenting sort of a screen in front of somebody while they're driving. So it could be like see-through, it's called like augmented reality stuff, where you're seeing through, like there's an extra layer added onto your visual system. Like you see a projection of this is where you're going to turn next, or just even looking at your phone as you're navigating directions. If your eyes have to move back and forth between a few different things, that task, they're both demanding of your visual resources, so it becomes more difficult. Whereas if it was presented to you auditorily, it might become easier, and then you have a lot of other things that are adding on that are all trying to get your attention at the same time. So I guess an example while driving is now some cars are coming with the seats vibrate to tell you information. So instead of hearing more things, instead of seeing more things, it's haptic, so your body is feeling it. That uses different resource pools. So it makes it safer or makes it easier for you to process that at the same time. So this gets into that central executive, that working part in the middle. If you have this task where first you so the faces are relevant in the first task. You're supposed to remember the faces that are cued to you, but not pay any attention to the scenes. So the images that are presented, either a face or a scene or a face or a scene. And then you're supposed to test if you've seen the face before, something like that, within that trial. So either you're supposed to identify faces So this is all done in a scanner, I should say. So you're brain scanning while you're doing this. So first task, you're supposed to try to remember faces, but not pay any attention to the scenes. In the second task, you're just passively viewing. You're not supposed to pay attention to the faces or the scenes. It doesn't matter. Once you are in the other trial, there's just the stimuli of an arrow, so it's not faces or scenes.
So is the central executive in that case the ability to control your attention?
Absolutely. It's that ability to control what's coming in from the different sides, what you're referencing in your long-term memory. So it's kind of that pooling of all of the necessary elements and sort of being able to use them and make decisions about that. Great question. So the results of this study was that there are differences in individuals that give them a greater or lesser capacity to use that central executive. So people who were able to I correctly identify the faces within this trial, so they were better at doing the first task, were also the people that had less activation when they were seeing the scenes. So you could see from the scanner that the people that performed better were able to pay attention to faces more and also drop that attention for the scenes, whereas people who just had the same type of, they have a lot of activation, even though they're supposed to only pay attention to people, they're also paying attention to the scenes. They're doing a poorer job correctly identifying the faces. So the condition of good suppressors are people that have less activation for the spaces. The poor suppressor, the people that have activation for the scenes. I don't know if I said that right, but you see what I'm talking about? Okay. So working memory and the brain. This is cognitive, and it's nice to look at the physiological side of things. So also looking at brain scanning and physiological experiments, we can sort of identify the parts of the brain that are active and are useful in these memory processes. So when it comes to working memory, the prefrontal temporal areas are involved in this process. So you have the frontal cortex, also the prefrontal cortex is a little bit more inward, the amygdala and the hippocampus. So here was an experiment. The monkeys were shown the food either on the right side or the left side of them, and then a screen was put up, and those things were covered. So there's a delay in between when they're presented with where the food is and where they have to identify where it is. So then once the screen is removed, the food and the garbage spot are both covered, and the monkey has to remember where the food was. So if they removed the prefrontal cortex, animal studies, they do this type of thing. If they did that, the monkeys weren't able to correctly guess which side. It was just a chance rate that they would correctly identify where the food was. So that tells you a little bit about the prefrontal cortex is useful in keeping information in your short-term or your working memory. There was also, they used, I think this is it's either the prefrontal or parietal. It's written in your book. Actually, I'll find that so I know. But essentially, you have a similar type of task where you're looking at a specific neuron. When a square appears, you have that electrical activity for those neurons that are sensitive to the location of the target. In the next section, the target goes away completely, but since we remembered sort of that location of the target, that neuron still is firing. And then when the fixation cross itself, what you're supposed to be looking at, once that disappears, the eyes will actually move towards the area where the stimulus first appeared. So that gives you even a little more justification that this short-term memory process is occurring. That part of your brain that's active in actually seeing the task is still active when it's removed and you have that memory process. I just want to show you. prefrontal cortex, this one still. So it's neurons in the prefrontal cortex. So basically, other experiments, there's activation throughout your brain. It's not one location at a time. It's actually an interplay between different brain regions, different neural activity. So memory areas in the brain that we've identified are kind of here. So working memory takes place prefrontal cortex, parietal areas, and cerebellum, just from our imaging studies. Okay, so summary of the information. Memory is the process involved in retaining, retrieving, and using information about stimuli. It's very important. It's helpful to us. It encodes who we are as people, our experiences. This modal memory model consists of 3 structural features: sensory memory, short-term memory, and long-term memory. Sensory memory has no capacity limits, hypothetically, so you can take in all of that information, but it only stays for a very short time, between somewhere around 1 second and 2 seconds for different types of information. Short-term memory has limited capacities, so it can store something between 5 and 9, 7 plus or minus 2 chunks of information. So it could be the letters, it could be the words, it could be the sentences. So, and the duration is about 15 to 20 seconds. Your capacity of your short-term memory, when you're combining things, you can increase what's stored within that short-term memory by chunking pieces of information in meaningful ways. Information in your short-term memory can be coded in terms of sound, vision, and meaning. Your working memory is used to store and to manipulate information. So that's that extra, replace short-term memory with working memory and that executive function. So working memory consists of 3 components: the phonological loop, the visuospatial sketchpad, and the central executive. And working memory functions are executed mainly by the prefrontal cortex, but there are other areas, the parietal areas and the cerebellum, involved as well. That's actually all we had to cover for today, so you get to leave early. Okay.